thank you for inviting me. So I was here for the first 2 times when this event was happening, and I really wanted to present. So this is great to be here and also seeing you. Yes. Okay. Maybe okay. I would love to be in Koç giving this presentation face to face. But as you said, this is also very nice. So my friends from Koç are here, from Boğaziçi, and also from Hamburg here. So, okay, what I am going to talk about today. So, yes, in general, I will talk about the n equals to 4 super Yang-Mills and n equals to 2 superconformal field theories, integrabilities. Okay, but in particular, I will just talk about the coordinate Bethe ansatz solutions. So getting this S-matrices explicitly. So everything that I will say about these 2 theories will be wrapped around this coordinate Bethe ansatz technique. And yes, after spending most of my talk on how we understand this S-matrix solution so far, then I will talk about this new turn that maybe we can take on integrability by mentioning or yes, trying to explain, convince you about this Yang-Baxter, the relation between the Yang-Baxter equation and the quasi-Yang-Baxter equation. So yes, throughout the talk, I didn't give any references. So partly this is because I was lazy, and partly this is because that we have this very well written review that you can see here. Maybe I can also try to use. Yes. Here you already see this, but yes, I'm trying to get the disappearing. Yes, review is here. This is written by my advisor, and we are doing all these things together. Okay. Okay. So first, even before introducing this coordinate Bethe ansatz technique, I will just name the S-matrices. I'm sure that you all heard about it one way or another. So this S-matrices captures a great part of the dynamics of the scattering events of in and out states. But since we are talking about in and out states, I just want to highlight that we are always discussing the asymptotic behaviors of our field theories. So nicely enough, in 2D quantum field theories, it's often possible to calculate this exact S-matrices. And okay, how can we calculate this S-matrices? So to determine the energy spectrums of our theories, we can solve this eigenvalue problems with Hamiltonian. But if we impose this coordinate Bethe ansatz technique, and if we try to generalize the momentum states to n particles, then assume that we know the energy spectrums, then we can turn this eigenvalue problem to something that eigenvalue problem to this equations that we solve for getting the exact S-matrices. Yes, and I will give you examples about this coordinate Bethe ansatz. But before that, what I mean when I say a theory is integrable. So an integrable theory in a scattering event has this 3 very nice properties. So in every scattering event, particle number should be conserved, and the total momentum doesn't change but gets redistributed. And yes, this last one is holding the base for the Yang-Baxter equation or all this integrability discussion, actually, that the multi-particle state S-matrices factorizes. So what does this mean? So if I have this S-matrix to describe an n-particle state, then I can rewrite this S-matrix, or I can describe this event that is happening by just using two-particle scattering. So yes, I just wanted to have this not very rigorous, but still a nice algebraic discussion definition here. So just to let you know that the mathematical structure behind is very, very well studied, very well defined. So whenever we are talking about a state, a momentum state or a position state, we are talking about this elements of this tensor product space, right? And all this entries of the tensor product space are looking like this complex spaces. And in this case, S matrices, the two-particle S matrices is just this elements from the endomorphism. So here, I just wanted to start giving you very, very basic pictures. So I already said this factorizability thing is a very fundamental, important thing, right? If we only consider a three-particle scattering event, then we should describe this three-particle scattering as a scattering of tuples. So here, since we are doing everything pictorially, the order of the momentums are important. So, but there are two ways to describe this three-particle permutation in a sense with two-particle S matrices. And in order to have this consistent picture, these two ways that I written in the equation here should be equal to each other. And this is what we call the Yang-Baxter equation. Yes. Okay. Let's give the most basic coordinate Bethe ansatz example so that we would be in the same page. So if we are looking at a theory which has only one particle type and two particle states, this two particle momentum state, and momentums are P1, P2, then we can impose this ansatz. Yes, and this is what I'm calling the coordinate Bethe ansatz. That every particle can be written with this coefficient in front by just specifying the positions in the chain of the particles, and having this coefficients in front, that I also introduced the S matrices inside, and okay, assuming that unitarity for S matrices holds such that SP2 P1 is the inverse of SP1 P2, then we get the definition, this S matrix as an operator definition. We get this, and this from this definition on the states, the eigenvalue problem arises. And okay, I will show you the solutions of this coordinate Bethe ansatz for n equals to 2 super Yang-Mills, and also n equals to 2 superconformal field theory solution. But before that, yes, just to give you the complete general picture, I have to talk about what is this n equals to 4 super Yang-Mills is. So yes, this first statement is like the slogan of integrability people, right? The fact that n equals to 4 super Yang-Mills is integrable. Yes, we will see in a minute how it's integrable, in the sense that we can have the S matrices. So in this theory, we only have, so this is the maximum number of supersymmetry you can have in 4D, right? We only have the vector multiplet here. X's, I just want to specify them. X's are the real scalar fields. And when we talk about the spin chain in this context, then we are talking about the single trace operator, which means that we can compose fields as many as we want, but then we have to trace them depending on only one operator, so that we would get a spin chain structure, as we are already familiar with from this integrable models setting. And we won't be concerned with this last fact here, but the spin chains are being used to compute the anomalous dimensions. And what are these anomalous dimensions? So we are in a conformal theory. So we only look at the 2-point correlation functions, and delta is the thing that we are concerned, this anomalous dimension. And delta capital 0 is already coming from the classical theory, but we want to calculate this gamma, the quantum corrections. And yes, I'm always telling you that we are in the planar limit. This means that we are taking the color group n to infinity. And there are different ways to take this limit. N goes to infinity. I won't be talking about them, but yes. So okay, there are ways to take this limit. There are also ways to choose the vacuum, so that we can talk about spin chain structure. But I'm just interested in this one particular example, which is a SU2 sector inside this theory. We are choosing our vacuum as this ZL, which is just a scalar field, and then our states, this spin chain states are like this, as you can see here, the trace of X's and Z's, and yes, this is looking like a spin up-down spin chain already, and this is what we want to see anyway. So if we compute the Hamiltonian for this small sector, we will see that this is just identity minus the permutation operator. This P is the permutation operator here. And this is, we know this already. This is the nearest neighbor interaction Hamiltonian in the Heisenberg spin chains, this HXXX, the isotropic model, right? And yes, this is the Hamiltonian. So since we have the Hamiltonian, let's solve the Bethe ansatz equations. In this one magnon case, we don't see any S-matrices, right? Because we only have one particle, no scattering is possible. So we solve we act by the Hamiltonian to the state. And okay, just a small detail, since I gave you the Hamiltonian of just two near neighbor sites, then we act on this momentum states one by one for each two sides next to each other. Then we solve the eigenvalue problem, and yes, nicely enough, obtain the dispersion relation that we like very much. But when we come to the two-magnon problem, this is getting a bit complicated, but not that complicated. I just wrote it a bit messy. We have this Bethe ansatz, including the S-matrix, and then we impose here. This was the thing that I was talking about before. So we impose the eigenvalues into the equation, then solve for the S-matrices. And get this S-matrix definition, and we were expecting this because I already told you that this is looking like an HXXX, right? And I didn't write it here, but it's really, really easy to see that this S-matrices satisfy the Yang-Baxter relation. And it's already commutative, so no problem. So yes, theory is integrable. Okay, but when we go to do n equals to 2 cases, so I'm again interested in this particular example. So this first thing that you see here, this one blob, is depicting the n equals to 4 Super-Yang-Mills theory. So we are looking at the orbifold daughters. I really like to say this, the orbifold daughters of the n equals to 4 theory. What we do to obtain this n equals to 2 theories is orbifolding and marginally deforming, which means that actually, okay, I just want you to tell, I just want to tell the story. So imagine as if we are cutting this one loop here, and then combining how many we want of these blobs next to each other to get this reduced supersymmetric theories. So in this case, we are only combining 2 blobs, and this orbifolding process is basically this. So if you think about in terms of the component fields, then we are just multiplying the component fields from with a matrix tau, which only includes the e to I something, this unit things, so that we are producing more of those component fields. And when we do this, the number of supersymmetric charges reduces, but the conformal symmetry stays there. This is important for us. And we get after the orbifolding, we get this Z2 theory. So this is not the Z2 theory, the Z2 quiver theory, because as I wrote here, the coupling constants in the Z2 theory should be equal to each other. So this okay, maybe I should have say this before. So this blobs are representing the vector multiplets, and these lines going between them are the hypermultiplets. So for the first type we have G, and after orbifolding we get a G theory. But then we do this marginal deforming, which is basically just changing the second G to G tilde. And then we get this n equals to 2 theory that I wanted to talk about. And in this theory, again, we have some fields. I'm only interested in the in a way SU2 sector with this Q tildes, phi tildes. Q and Q tildes are coming from the bifundamental inside this hypermultiplet. They are some kind of fields, right? And phi hats are coming again from the scalar fields inside the hypers. But since we are doing this marginal deforming, and also we are in the planar limit, we have 2 possible spin chain structures, as I wrote here. So yes, we will compute the Hamiltonian with respect to these 2 types of spin chains. Yes, okay. I gave you the Hamiltonian here. Yes. So, okay, inside the Hamiltonian, since we have these 2 different type of spin chains possible, we see these 2 blocks of interactions, let's say. right? So this is the one block is looking like an this time hxxz, and the other one is again looking like an hxxz, which means that we again seeing this nearest neighbor interactions, but the anisotropic case. And yes, so if we again do this solving the Bethe ansatz equation thing, this time we get two S-matrices, which is dependent on kappa. And if you ask me what is this kappa, kappa is just G over G tilde. It's this ratio that we have. And then we would obtain this two S-matrices after solving the two-magnon problem. But this doesn't mean that this theory is integrable, right? Because we didn't check if the Yang-Baxter equation holds, or equivalently, we can check if we can solve this Bethe ansatz problem for three magnons. So we try to do that, but unfortunately, these two S-matrices cannot solve the Yang-Baxter equation. So this is why, okay, let me check, yes. So this is why that in the literature, n equals to 2 theories, this superconformal field theories are considered not integrable, non-integrable. So far, I gave you the general picture, the recent literature. What was the discussion behind this integrability, saying that n equals to 4 is integrable and n equals to 2 is not integrable. But okay, for our research, what we did was looking at this Hamiltonian more closely. So we see these two hxxz parts, and okay, they should be integrable separately. And this makes sense because this marginally deforming that I told you, this just changing the coupling constant of one side to G tilde is really coming into life as this kappas inside the Hamiltonian. So if we would only focus on one part, so we had this hxxx, the isotropic model before. So we did the marginal deformation. Then now we see the anisotropic model. So this makes sense, and this should be integrable. But we have two of the same this anisotropic parts in one Hamiltonian. So somehow they are forming this weirdly twisted Hamiltonian. So this integrability falls apart. And okay, this being twisted thing was intentional because the marginal deformation is easily can be seen by this kappas appearing in the Hamiltonian. But the orbifolding part, this combining the copies of same theory in an orbifold version is corresponding to this being twisted part. And yes, okay, by the way, if you only think about what this orbifold word means in the like less advanced geometrical way, then this is just having maybe a sphere. So sphere has this x square, let's say the x square plus y square equals to 1, right? The orbifold version of this would be b square x squared plus y squared over b squared equals to 1. So we create, and b is just a constant. So we create this twist, and we call this only in the geometrical sense orbifolding. So again, we try to understand how this twist can lead to integrable theory. But for this, we need to expand the definition of integrability in a sense. This was the idea behind the calculations. So yes. So for the last 10 minutes, I will just speculate on this diagrams. So on the left, we see the picture of the Yang-Baxter equation, right? There are two ways to get this permutation from 1 to 3 to 3 to 1, and these should be equivalent. But we also know that there is this other version exists recently. We know this recently. That so okay. When we try to give this mathematical description to the Yang-Baxter equation or this Yang-Baxter algebra in general, these are being done with Hopf algebras, right? So yes, if you don't know about them, just don't care about them. But there is also other types of algebras which are very close to Hopf algebras, but they are not, because we lose very nice properties like associativity in the Hopf algebra. So then there's this thing also called Dünfeld twists. So we can, if we have an S-matrix, this S-matrix formalism, then we can create a twist inside the algebra, and then we would need to again describe this three-particle permutation, the phi's, this little phi's, which are called the Coassociators, inside the process, so that we would obtain at the end this permutation. So right now we are trying to argue that yes, okay, this n equals to 2 theory is not integrable in the Yang-Baxter sense, but maybe it's integrable in the quasi-Yang-Baxter. The second equation is called the quasi-Yang-Baxter equation, the quasi-Yang-Baxter sense. So okay, how could we do this? Again, solving this different Bethe ansatz solutions and showing that they satisfy this second equation. Okay. By the way, if you just want to know how this quasi-Yang-Baxter equation looks like, which is apparent from the picture anyway, but this S phi S structure. So okay, so far we have this one solution, and we are trying to make the number of solutions larger and trying to understand this possible solutions better. So what should we do? So I already told you from one angle that this S-matrices from n equals to 2 theory is not satisfying the Yang-Baxter equation. And okay, this also means that we cannot solve this problem in three-magnon case, right? Because in the three-magnon case, we would have the S1, 2, S2, 3, but also S1, 3, which exactly means the permutation of 1, 2, 3 to permutation, the permuting 1, 2, 3 to 3 to 1. So this three-magnon Bethe ansatz is not solvable in the n equals to 2 case, but we can do this. This is the easiest way. So we can add contact terms inside the let's say the coordinate Bethe ansatz that we have, such that each time we see this exponential term, we not only get the S-matrices, but this contact terms with a coefficient and a delta function, which are just coming to life when this x1 and x2 or x2 and x3 are next to each other. this is the closest thing that you can have to a coordinate Bethe ansatz, but it's not the same thing. So this is what we did. So we solved the coordinate Bethe ansatz with contact terms and obtain a solution. So okay, since we have an exact solution right now, this means that this should correspond to integrability in a sense, but not the thing that we are used to. And okay, the other way would be having this two. Maybe I should write this. So this, sorry. P1 and P2 are going in the scattering event, but also there is this other couple, let's say, that going into the scattering event together again. And then we can impose these conditions on the, for example, the conservation of momentum, conservation of energy kind of conditions to somehow imitate this idea of twist in this momentum states. So yes, this is what we are trying to do now. And okay, after doing this, then we would get this new Yang-Baxter quasi-Yang-Baxter equation, and somehow expand this understanding on the integrability. I mostly wanted to talk about the motivation behind this calculations, so I didn't give you any results. Okay, I hope that this was an interesting talk. Thank you for listening.